Hi everyone. So welcome to this supplementary video. In this video, essentially, I'll be practicing the exam, which is on Canvas. So do try to practice this on your own. And this video is just to give you an example of how to approach an exam and how to kind of think about problems. And I'll try my best to sort of like be in your shoes and give you an idea of how to approach such questions. This video will be in two parts. In the first part, I will be doing the part one of the exam, and then the second part, I'll be doing the second part. All right, so let's begin. So this practice exam is 75 minutes, like your exam one. There are 7 problems, 10 pages, so something to keep in mind. This video will focus on part one, where there are short questions. So there is some short explanation that has to be provided. Clearly, it doesn't have to be long. And the explanation could be in the form of text, derivation, or a calculation. And the credit will not be given just for selecting the option. So some work has to be shown. It doesn't have to be detailed, but it has to be clear of what you were trying to think about. And then there's sort of a comment that you shouldn't try to spend more than 25 minutes on the conceptual questions, 5 minutes each. So about 30 minutes, 25 to 30 minutes. And the remaining time you should try to budget for the long problems. This is, of course, an approximate number to keep in mind. And then there is a comment about if you need more space, you can always write on the back. All right. So let's start. So the first question says, what are the dimensions of rho v L by mu? Rho is density, v is velocity, L is length, and mu is the viscosity. So this is pretty a standard dimensional analysis problem, and you have done something similar in the homeworks. So typically to approach such problems, we simply say, we'll just do the dimensions of each. So this is dimensions of rho times velocity times length by dimensions of viscosity. Dimensions of density is mass per length cube, kg per meter cube. So ml minus 3. ml minus 3. And then we have velocity. Velocity is meters per second. That is LT minus 1. Then I have length, simply length as dimensions. And then there is viscosity. And that's probably where some students may not remember it, but this is a good thing to remember. ml minus 1, T minus 1, which is the dimensions of viscosity. You will have your cheat sheet, so hopefully you can look it up if you don't remember right away. And so if you multiply, we have L3 into L into L. The numerator now has L squared times L minus 3, which becomes L minus 1. This is ml minus 1, T minus 1 by ml minus 1, T minus 1. This gets cancelled. This is 1. So clearly this is dimensionless. Okay. So that's it. So this is all you have to do in problem 1. So dimensions are dimensionless. All right. So let's go on to the second problem. Now it says, consider a stationary block submerged inside water. So clearly this problem is of a stationary block. So something like hydrostatics. That's how we have to think. And what is the direction of pressure force applied by the water on the two inclined faces? So it's asking for direction of the direction. So it's not asking for the magnitude. So I don't necessarily have to do a calculation. Pressure force applied by the water on the inclined faces. So basically these clearly are some two faces here I see. And we have to find the pressure force combined, and then there is a note which says that they are not asking you to find a direction of total force on all the faces, but the sum of force on the two inclined faces. So basically, the question is saying that there are more faces in the system, just a block, but it's only interested in understanding the force on these two faces. So if the pressure force was on all the faces, it becomes the buoyancy force. But it's not asking us to do that. It's asking us to only find the force on the phase 1 and phase 2. So essentially phase 1 is like this, phase 2 is like this. We know the force by water is push direction, right? And normal. Basically, I'm sketching phase 1 on the left here. It's saying it's pushing. So basically, it's pushing downwards and then inclined. But as one can expect, the inclined forces, the horizontal forces have to cancel out because we know they don't stay. If there is a horizontal force, there is nothing like gravity to balance it. So it will essentially start to move in the horizontal direction. It's stationary, so the horizontal forces will cancel out. And essentially, we will get a negative downward force. So it's a negative z based on that convention, which makes it basically it's opposing gravity. And why is that? Because again, the faces are like this. Note if this was buoyancy force, we will also add on the forces on here and here. And in that case, the bottom force will have such a large upward force that it will kind of make it net positive. But right now it was only on the side forces. So that's where I think most students might get confused and might end up selecting positive Z, but that's for the buoyancy force. Here we are only asking for part of what goes into buoyancy force, that is phase 1 and phase 2 on the inclined part. So the explanation could just simply be, it's normal, horizontal force cancels out, and then like the sketch is enough to just kind of explain the thinking. Again, it doesn't have to be too detailed. We just have to understand why you selected what you selected, and you credit correctly. But it cannot be like just select without any explanation. Okay, that's not going to earn you marks. All right, third problem. It's saying water is flowing horizontally through a converging duct from left to right. So water is flowing. So clearly this is a Bernoulli's kind of problem because this is water is flowing now, right? Horizontally through converging duct from left to right. So I see here the area is higher than the area here. So it's converging. The cross section in the left portion is larger and area than the cross section in the right portion, which is the converging part, I guess. Two vertical tubes are attached to the duct to measure the pressures in the left and right regions of the duct respectively. Okay, so these tubes are essentially sort of acting as a pressure meter, and both tubes are filled with water only. So essentially this it's only water everywhere. Which of the following statement is correct and why? And this is the same height that has been given. Okay, so how can we approach this? So this is essentially saying there are two tubes which are measuring pressure essentially, and then we have been asked to find which one is okay. So the way to think about this is generally like we do, we see a point 1 here, a point 2 here, right? There is the same height, horizontally water flowing for this dotted line. We'll say P1 rho V1 square by 2 is equal to P2 plus rho V2 square by 2. Okay, so that's one point. Now, clearly, we also have A1 V1 is equal to A2 V2. And because the cross-sectional area in V2 is bigger, so A2 is less than A1 implies V2 is greater than V1, right? And so this number here is greater than this number, right? So this means because it has to be constant, that means P2 is less than P1. So just to clarify, so this is a sum of pressure energy plus kinetic energy, right? And we have done similar problems in class as well. The velocity is higher in the second portion because it's converging, it's a flowing system. So the pressure energy has to be less. In simple words, that's the case. So now if pressure is less, then I should expect the height of this height of water should be lower, right? Because it's supporting. Remember, it's hydrostatics now in the vertical direction because the water is not flowing. So it's essentially a measure of pressure, just the height is simply the measure of pressure. And because height is greater than the other height, that means it's indicating that the pressure there is higher. So this situation is not possible. Okay. This is a slightly more complex question than the ones we have seen before. So basically, the idea is think about Bernoulli's, it's a flowing problem, and think of continuity. Again, it's a flowing problem. So we have P1 plus OV1 square by 2 is equal to P2 plus OV2 square by 2 is equal to A1 V1 is equal to A2 V2. So that means that velocity is bigger, which means pressure is lower. And if the pressure is lower, then I should have a smaller height of the column. But I have a larger height, so it is not possible because that means that the pressure there is higher, which is not true. We just found the pressure is lower. Okay. So the explanation could be, just like the ones I have on the screen, or you could just say in text. You can even say, oh, pressure 2 is lower because kinetic energy is higher. So the situation is not possible. So that is also acceptable, just to give you an idea as you're thinking about how to attempt in your exam. All right. Then the question is, which of the following describes the velocity profile below? So I see an x and y. So this is two-dimensional plot, and this is classical question for velocity profile, like the ones in clicker questions. So what I see is all the arrows are pointing in the same direction. So first, the direction does not change with x and y. They are all pointing in the same direction. Moreover, I also see that the length is also similar. So they're also seemingly the same magnitude. So if I have x plus y here, this cannot be, because this would mean that for a different negative positive x, I will have a different direction. This also doesn't work. X square plus y square, it will yield a positive answer everywhere. But then I am not changing the magnitude because, so like, yeah, so this also doesn't make sense. So this is the answer. It's the same direction. And so this problem generally is through elimination. And so that's enough, right? You don't have to explain too much, the same direction. That's why you selected this. In such problems, sometimes explanations is not very concrete, so you don't have to worry too much about it. Just, whatever you think clearly indicates it, you can select it. You don't have to go and elaborate and waste a lot of time in explaining. We understand it's in these kind of plot problems, it's mostly by elimination, and you can select the answer. All right, so let's keep going for the last practice problem for conceptual part. So now it says, consider a velocity profile v vector is equal to v naught into 1 minus I square I cap, I hat. Which of the following options correctly describes the acceleration in the fluid? This is an classic acceleration problem. So we do know that acceleration is del v vector by del t plus material derivative essentially, or v dot del v, right? This problem is only for I hat. So clearly I only have one component of the velocity. So we know that essentially this will be du by dt essentially. And then ay would be dv by dt. I don't see even the third component even mentioned. And so remember that velocity vector is u I hat is vj hat. But velocity y is simply 0. So this goes away. And if there is no velocity in the y direction, there cannot be acceleration in the y direction. So this is simply 0. So the main thing I have now is the acceleration in the x direction. So then ax becomes du by dt is equal to del u by del t plus u del u by del x plus v del u by del y. Right? So when you see such problems, the best thing to do is simply start to cross out terms. So here del u by del t is 0 because the time dependence is not there. You also know that this is equal to 0 because velocity v is 0. So the term I'm left with mainly is u du by dx. So ax is u del u by del x. And that's my velocity. U is actually velocity u, as you can see here on the top, does not even depend on x. It's only a function of y. So I can simply say this also goes to 0. So this is 0. Okay, so I do have the answer. It's a 0 I had. Okay, so just have to be a little careful in doing these math problems, but clearly this is um, fine. Okay, so in the second part of the video, I will go through the long problems, but hopefully this was helpful for you to see what we're looking for and also to get some practice. And I look forward to seeing you in the next video.